In this section, we are going to consider the sum of two independent continuous random variables and how this affects the expected value and the variance. We have previously seen this result, that if we have two independent Poisson distributions, then the sum of these two distributions will itself be a Poisson distribution. So in other words, if x and y both have a Poisson distribution, then x plus y will also have a Poisson distribution with a lambda value of lambda x plus lambda y. In this case, the lambda value represents the expected value of the distribution. So from this we can conclude that if lambda is the expected value of x, then the expected value of x plus the expected value of y is the expected value of x plus y. We can also use the result that the variance of x plus the variance of y is the variance of x plus y. It turns out this result is not unique to the Poisson distribution, and it's actually true for any independent, discrete or continuous random variables. So we can use these two results in calculations. In this example, we're going to consider the volume of lemonade that Chris purchases in a supermarket. This is a discrete random variable denoted by S. The mean is 4,000 millilitres and the standard deviation is 1,000 millilitres. The reason this will be a discrete random variable is because lemonade is only sold in certain size bottles, so it wouldn't be continuous because he couldn't purchase any amount that he liked. The volume that he then drinks on the way home would be a continuous random variable. This is denoted by J. And the mean is 300 millilitres, the standard deviation is 100 millilitres. We're going to assume that J is independent from S. R is then the random variable, the amount of lemonade that is left in the bottle after his journey. So we're going to start by defining R, the amount remaining, as S, the amount he purchases, minus J, the amount he consumes. We're going to write this as S plus minus J in order to get this in the form that we need it to be in. So for part A, we first of all want the expected value of R. We can use the formula that this is the expected value of S plus the expected value of negative J. Then using the expected value of AX plus B formula, we can write this as the expected value of S plus minus 1 times the expected value of J. This is therefore 4,000 plus minus 1 times 300, which is 3,700 millilitres. The expected value of the amount remaining after the journey is 3,700 millilitres. We're now going to consider, first of all, the variance of R. So the variance of R can be found using the variance of S plus the variance of negative J. So this would be the variance of S. And again, using the AX plus B formula, this is going to become A squared times the variance. So we're going to have minus 1 squared times the variance of J. So this is actually just the variance of S plus the variance of J. So we've got standard deviations here, so we need to square these. So the variance of S is going to be 1,000 squared. The variance of J is going to be 100 squared. So this gives us 1,010,000. So therefore, the standard deviation of R is going to be the square root of this, which is, to 4 significant figures, about 1,005. For part B, we need to consider whether it's realistic that the assumption that J and S are independent. We could consider, for example, the fact that if Chris is very thirsty, he may purchase more and therefore drink more. We could also consider the fact that depending on how much he purchases, he may not then be able to drink that amount. If he purchases a small amount, he may be limited to how much he can drink. So for those reasons, they may not be independent. Here, any sensible reason is fine. Now complete exercise 4D on page 66.